Good morning. My name is Prashant. Today, my presentation is on Toward a Universal Quantum Programming Language. Introduction to Quantum Computing. Quantum Computing Overview. Quantum computing is a new paradigm that leverages the principles of quantum mechanics to process information in ways classical computers cannot. Instead of using bits, which represent data as zeros and ones, computers use quantum bits, qubits, that can exist in multiple states simultaneously due to superposition. Core quantum principles. Superposition. Superposition allows qubits to represent both 0 and 1 simultaneously, enabling massively parallel computational possibilities. Entanglement. While qubits are entangled, the state of one qubit is directly related to the state of another qubit, regardless of the distance between those two qubits. This allows for faster than classical correlations and enhanced computer power. Quantum interference. Quantum computations leverage interference patterns to amplify correct solutions and cancel out incorrect ones. Potential impact. Quantum computing has applications in cryptography, drug discovery, material sciences, AI, and optimization. These applications could revolutionize industries by solving problems previously considered computationally impossible or infeasible. Now, what is quantum programming language? A quantum programming language (QPL) is a specially designed programming language to program quantum computers, allowing users to define quantum algorithms and operations in a way that quantum hardware can execute. These languages enable the expression of quantum phenomenon and manage unique quantum computation constraints. Examples of current computing quantum languages are QL's SCIT IBM from IBM, an open source framework for working with IBM's quantum computers. Cirq from Google, a Python based library for creating, simulating, and running quantum circuits on Google's quantum processors. QHash, Microsoft, a language focused on quantum computing integrated into Microsoft's Quantum Development Kit, QDK. Quipper, a functional quantum programming language used for defining quantum circuits. Specialized syntax and operations. Quantum programming languages need specialized syntax for defining quantum gates, circuits, measurements, and managing qubit states. This includes the ability to perform operations such as Hadamard, C0, T gates, and measurements, which are unique to quantum computing. So, why a universal quantum computing? Why do we need it? Because of the following reasons: standardization, portability, collaboration and sharing, and reduced complexity. Let's look at each. Standardization. A universal language which establishes standardized practices, reducing the variability and incompatibility that currently exists across different quantum platforms and languages. Standardization simply simplifies the learning, and using quantum computing, it makes it accessible to a broader range of developers. Portability. A universal language would enable code to be easily transferable across different quantum hardware platforms, eliminating the need to rewrite or modify code significantly for each type of quantum processor. This portability would allow researchers and developers to switch hardware providers or test their code on various platforms without needing extensive adjustments. Collaboration and sharing. With a single language, the quantum computing community will collaborate more effectively, sharing algorithms, libraries, and resources without worrying about the compatibility rules. This could lead to faster advancements as researchers can build on each other's work more easily. Reduced complexity. A universal language would abstract many of the low-level details of quantum computing, allowing developers to focus on designing algorithms rather than dealing with hardware-specific issues. Now, what are the challenges in developing a universal quantum language? There are many, like hardware variability. Quantum computers are built using various physical systems such as superconducting qubits, trapped ions, and photonic qubits. Each type has unique characteristics, including different gate sets, coherence times, and error rates. Creating a language that can accommodate to all these different architectures without compromising performance is a significant challenge. Low-level abstraction. Quantum computing operations happen at much lower rate than classical computing. Quantum languages need to control qubit states, entanglement, and measurements directly, which makes creating universal high-level abstractions difficult. Error-prone nature. Quantum computers are highly prone to errors due to decoherence and noise. The error correction methods required vary by hardware, making it challenging to create a universal approach to error management within a single language. Performance differences. Optimizations that work for one type of quantum hardware may not be applied to another. For instance, the code optimized for trapped ion systems might perform poorly on superconducting qubits. This complicates the goal of languages that can efficiently execute on all hardware. Now, requirements for universal quantum language. Abstraction layer. The language should offer an abstraction layer that hides the hardware specific details, allowing developers to write code without knowing the specifics of hardware. This layer should automatically handle low-level operations like qubit initialization and measurements, making programming simpler. Hardware agnostic compilation. The language should be able to compile high-level code into machine code that can run on quantum hardware. This compiler would need to translate generic quantum operations into specific gates and sequence supported by different quantum numbers. Support for hybrid computation. Many quantum algorithms, especially in the near term, rely on hybrid computation where quantum and classical resources are used together. The universal language should facilitate seamless integration of quantum and classical operations, allowing developers to create complex hybrid algorithms. Error corrections and fault tolerance. Error correction is essential for reliable quantum computing. A universal language should include built-in error correction methods or libraries that can adapt to different types of quantum hardware. This involves standardized error correcting codes or fault tolerant protocols. Now, what are the current approaches and languages? Now, Qiskit from IBM. It is the Qiskit language strong in quantum circuit construction and supports IBM's hardware natively. It offers modular libraries for algorithms optimization and machine learning. Now, Cirq from Google. Designed to work with Google's Sycamore processor, it focuses on fine-tuning and customizing quantum circuits. QHash from Microsoft. It is part of the Microsoft Quantum Development Kit with specialized libraries for quantum cryptography, chemistry, and more. Kuiper. It is a functional language with strong capabilities in defining and manipulating complex quantum circuits. But there are some limitations to these languages, like each language is primarily designed for their own specific hardware, limiting the compatibility. There is a lack of standardization in syntax, semantics, and supposed quantum operations, creating barriers for cross-platform work. Okay. Now, what are the essential features of universal quantum language? There are a few like interpretability, high-level constructs, extensibility, modular, and scalability. Okay. Now let us look at each. Interpretability. The language should function across platforms, allowing code written in the universal language to execute on any quantum processor. This will likely involve standardized APIs and middleware to communicate with various hardware architectures. High-level constructs. Provide high-level functions to provide common quantum operations like initializing qubits, entangling states, and applying gates, without needing detailed knowledge of the underlying mechanics. This would simplify the development of algorithms for research without deep quantum expertise. Extensibility. The language should allow developers to define new quantum operations and algorithms, making it adaptable as quantum computing evolves. Extensibility would enable third-party such as hardware vendors to add custom optimizations or hardware-specific features. Modularity and scalability. Support modular programming, enabling complex quantum applications to be built from smaller reusable components. Scalability is crucial as the number of qubits increasing, allowing for development of larger more complex quantum algorithms increases. Now, what is the role of compiler and middleware? Middleware, quantum compiler, translates high-level language instructions into machine-level instructions specific to each quantum computer. Compiler must map logical qubits to physical qubits on the device, optimizing the allocation to minimize decoherence and gate logics. Middleware layer. Middleware could manage communication between the universal language and various hardware platforms, allowing code to be optimized for each platform's specific requirements. This layer would abstract hardware details, providing error management and support hybrid operations, enabling seamless cross-platform execution. Okay, now what are the proposed framework for universal language? Core language features. It provides standardized syntax and semantics to define quantum states, applying quantum gases and perform measurements. It should include error correction methods, support for hybrid quantum classical tasks, and libraries for common quantum operations. Standard libraries. Libraries for standard quantum algorithms, error correction methods, and hybrid computation would make it easier to develop quantum applications without needing to build basic functionality from scratch. Extensible plugins. Hardware vendors would create plugins that optimize the language for their hardware, making it adaptable without altering their core language. Plugins could include custom qubit mapping strategies and optimized gate sequences and specialized error correction protocols. Now, what are the challenges and future directions? Hardware evolution. As quantum hardware continues to evolve, the language must adapt to new qubit types, error rates, and gates set to remain relevant. Error correction evolution. Developing standardized error correction methods across different types of quantum hardware is challenging but essential for reliable computation. Quantum classical integration. Hybrid computation, quantum and classical, is crucial for most near-term quantum algorithms, requiring seamless integration with the language, community, and industry support. Success depends on buy-in from both academia and industry, making collaboration essential for establishing standards and promoting adoption. Conclusion. Summary. A universal quantum programming language will address three challenges in portability, collaboration, and complexity reduction. It could democratize quantum programming and make quantum computing more accessible to developers around the world. Call to action. Encourage collaboration between the developers, researchers, and hardware manufacturers to work toward the development of universal language that can propel quantum computing forward. Thank you.